In the meantime, where we're going, we're not going to need servers. So let's jump right in here. As mentioned, hi, I'm Kevin Feasel, run a predictive analytics team out of Durham, North Carolina. And the last thing I want to mention on here is that I have a blog called Curated SQL. The idea behind Curated SQL is I try to find and link to 5 to 10 interesting posts per day on topics all across the data platform space. So that's curatedsql.com. What I'd like to get out of this talk, 4 separate things. The first one is to help you understand what exactly is a serverless SQL pool in Azure Synapse Analytics. Then we're going to talk about loading data into a serverless SQL pool and find out that's not actually possible, but we'll find a way. Because next, we're going to query data in a serverless SQL pool. And finally, get a feeling for how much all of this is going to cost, because that's an important topic. So let's start off with a brief overview of what exactly is Azure Synapse Analytics. This is Microsoft's platform for modern data warehousing. There are 3 separate components which make up Azure Synapse Analytics as it is today. The first component is called Azure Synapse Analytics Dedicated SQL Pools. It had a previous name, Azure SQL Data Warehouse. It is Microsoft's attempt to offer up a massive parallel processing solution for classic Kimball-style data warehouses. And when I say Kimball style, I mean fact dimensional style of model. So the whole point here is we're going to have data that's structured in a specific way that fits what a normal data warehouse would look like, but is pretty large. The minimum for a dedicated SQL pool that they recommend is that you have at least 1 terabyte of data. And usually we're talking about the largest fact table or the smallest fact tables. You know, some fact table somewhere has at least 1 billion rows of date and numeric data that you can slap a column store index on. Major dimension tables, generally not that big. You know, we may be talking about tens of thousands, hundreds of thousands, maybe millions of rows. Once you get to hundreds of millions or billions of rows in your dimension tables, things get a little icky, but that's okay. That's not a topic we're really going to talk about much tonight. The last bit of what constitutes a classic use case for a dedicated SQL pool is users are typically working off of what I would say is a set number of queries. You have known business problems, monthly reports, quarterly reports, year-end reports, reports that go to government agencies, to regulators, to shareholders, the types of things that are run periodically or at least come from the same class of problem. For example, we have this sales information, and you may ask different questions. Today, we want to learn about products that have these attributes. Tomorrow, it's products that have these attributes. But we can agree upon the attributes that are relevant for a product that we would be concerned about when it comes to getting sales data. The flip side of the coin is Azure Synapse Analytics Spark pools. These run Apache Spark clusters on demand, and you spin the thing up, you do whatever Spark processing you need to do, and quite often you shut the thing down when you're done. This is ideally suited for complicated data transformation that you don't really want to do in T-SQL. An example of that is a lot of text processing, working with regular expressions. Extremely painful to do in T-SQL, not painful to do in Scala or Python using Spark. You may also have some types of distributed machine learning operations, things that don't fit very well on a single machine, but can fit in memory on a fairly large number of machines. So there are some good uses for Spark pools, and we're not going to talk so much about comparing Spark pools to Azure Databricks or to HD Insight or to the half dozen methods that you can get a Spark cluster set up in Azure. That's a little afield from tonight's topic. Instead, we're going to go to the third side of the coin, which is serverless SQL pools. So serverless SQL pools are intended to be very different from dedicated SQL pools. First, your serverless SQL pool does not store data. There is no permanently stored information in here. You can't take a database backup, move it to somewhere else, restore that backup, and have data. You don't insert into tables in this serverless SQL pool because there's no place where it would go. Instead, you read files typically from Azure Data Lake Storage Gen 2. But you can also read data from a few other sources like Azure Cosmos DB. Now, serverless SQL pools, they don't require pre-configured infrastructure. When I set up a dedicated SQL pool, I'm configuring the data warehousing units, and those DWUs basically tell me how many machines are going to be available to me to process this work. There's no, I'm not going to say there's a direct formula that if I use DWU 5,000 that I get this many servers. But if I get DWU 10,000, I'm given a larger amount of processing capability. So we predefine what is the scope of processing capability versus the amount of money we're willing to pay for that processing capability and that storage of data. For serverless, instead, the pricing model is based off of data processed. And we'll talk about what data processing means near the end of the talk. But high level, $5 per terabyte of data processed US, and that's the only fee. You don't pay to have compute available to you. It is available on demand as you run the query, and all of the financing comes from the amount of data that is processed as a result of you sending a request, you writing a SQL query and it doing work and possibly giving you back a result set. This can be useful in a few places. The best example I can think of for a serverless SQL pool is data spelunking. Contrast this to the dedicated SQL pool, where I try to put you in the mindset of known business problems. We have these specific questions that need to be answered on a regular basis, or we have these general classes of questions. The spelunking motive is almost the opposite. I have no idea what the next request is going to come at me, but I do know it's somewhere in this data lake, and I need to find a way to translate that customer request to this data in the data lake. That's where a serverless SQL pool can be extremely good. Ad hoc processing, the types of things that I may not ask you twice for this data. I just need it once because I'm curious. And if I ask you 2, 3, 4 times, now that's a signal. If we have a dedicated SQL pool, if we have a warehouse, maybe some of this information needs to go to become available in that warehouse. But just because I asked you once doesn't mean we should spend 2 months or 2 sprints getting that information in here because, well, I may not need it again. But there are other uses for serverless SQL pools, and we'll talk a little bit about logical data warehousing, where we virtualize the storage of data and pretend that it's available in this serverless SQL pool like it would be in a dedicated SQL pool. We can do some simple transformation, some simple cleanup of data, especially changing data types and changing file formats, how we store the data. That kind of thing is actually really easy to do with a serverless SQL pool. And you can also use serverless SQL pools to query tables that have been created in a Spark pool. There is that level of cross-product operation. So before we get into those specific use cases, let's talk through very briefly how I might go about creating one of these serverless SQL pools. And obviously the first step is we create an Azure Synapse Analytics workspace. Once you create a workspace, turns out you get this built-in serverless SQL pool, and it's just right there for you. If I select new to create a new serverless SQL pool, it won't let me. It will allow me to create dedicated SQL pools, but I can only create, well, I can't create any serverless SQL pools. Now, there's also a delete option, but it will not work for that serverless SQL pool. So you cannot delete it. You cannot create new ones. You have the one, and that's the only one that you really need. But remember, just because you have it doesn't mean you're actually paying for it. You only pay for data processed through it. I can create an Azure Synapse Analytics workspace, and if I don't do anything with it, if I don't create those Spark pools or dedicated SQL pools, and I don't have any queries that run through the serverless SQL pool, I'm not paying anything. That doesn't get charged. So life is good there. So we have this thing. It's available for us. We want to query data. And our specific scenario takes us about 100 years in the future, where we have colonized and terraformed parts of Mars. So we are now members of the Martian Agricultural Data Collection and Ownership Committee. And we have agricultural plots that are located in different cities on Mars. Each of those plots has a series of IoT devices which transmit information on different agricultural measures that are of importance for growing crops. And we want to try to understand some of this data a little bit better. We've collected a lot of data over time, over a 5-year period, and want to put together what I would call a rapid access system for our committee members. And we've chosen Azure Synapse Analytics serverless SQL pools to do the job. Serverless SQL pools run off of a variant of T-SQL. It is mostly a subset of the T-SQL language that strips away some of the capabilities because not everything's supported in a serverless SQL pool. And part of that is because, well, they're almost entirely read-only. So I can't insert, update, delete, merge. I can't really do a lot of the data modification work. I am very limited in how I can create tables because I can't directly create a regular table and store information in there. Instead, what we have to do is access data that already exists somewhere else virtually. One of the easiest ways to do this is to store your data in Azure Data Lake Storage. And fortunately, with Azure Synapse Analytics, we have a storage account that is connected to our workspace. Either you've connected it, one that you've already created in the past, or as you create your workspace, this generates a new storage account for you. And you can use that storage account, store data in your new data lake. And for me, I'm going to store it over here in the Synapse folder underneath that CS Train Azure Data Lake Storage account. So we have data that is going to be in a data lake. We're going to be able to query that data. And the first way that we're going to query this data is using a command called openrowset. Openrowset allows you to read data from a folder or an individual file or a set of files. And in this command from openrowset, we're going to say essentially bulk load this data, load in scare quotes, from this particular location. I'm pulling it from a Mars Farming raw folder in my data lake. And inside there, I've got various scores. One of them is how arable is this soil? And I have that information for each of my roughly 9,000 plots at a 10-minute interval over the course of 5 years. Let's look at the first plot, which is arability score _1.text. Because this is text, it's actually a delimited text file. And the delimiter is a semicolon rather than a comma. So the format is CSV, but it's really semicolon delimited. And it has 3 columns. The first one is a plot ID. The second one is the date and time of the report. So when did this signal get sent out from the IoT device? And what is the score? What does that errability score measure? The whole result of this is a virtual table that I've named errability, and I'm going to select the top 10 results from it. And that'll give me back a result set. openrowset supports a few different data types. I just walked you through an example with CSV, or which I could rephrase to as delimited text. We can use the Parquet format. Parquet is a columnar data storage format. So CSV and other formats like Avro are row store. You have a row, a row, a row. Columnar formats are like column store indexes. You have each column is its own collection of data. So instead of storing a row's worth of data where you have one instance of each attribute, you collect all of the information about the attribute, and you collect all of the information about the next attribute. And this ends up compressing much better than a row stored data set would. You can load data in JSON format, but there's a little trick to that, which we'll talk about when we get there. And also Delta Lake. A Delta Lake, if you're not familiar with the term, is a concept that is owned by the Linux Foundation. It was originally created by Databricks and is intended to provide you serializable transaction support for data lakes, which means I can insert, update, delete, merge individual rows in a data lake or sets of rows in a data lake as though it were a relational database. And I can store that information. I can look at it over time. There's time travel, which is their term for essentially temporal data. So if you're familiar with temporal tables in SQL Server, where I can say, what did this data look like at this point in time? You get some similar functionality with Delta Lake. Because the data is stored in Parquet format, one of the other niceties, in addition to it being columnar, is that there is schema metadata. There's a little bit of metadata at the beginning of each file that essentially indicates here are the columns and data types, and other things like the number of rows, the number of columns. This is all pretty nice. What serverless SQL pools allow you to do is read this data. So you still can't insert, update, delete. But if you happen to use Delta Lake on a Spark cluster and you connect that storage account, which is storing the files in Delta Lake format, you can read them in the serverless SQL pool. Let's jump to a couple of quick demos just to reinforce some of these thoughts. So I'm going to pop open the first script. If the font size is a little bit too small, please let me know in chat and I can increase the font size. But if the font size is good, we'll roll with this. So first thing I want to talk about is databases. We have here one database called Mars Farming. And I do want to point out we have external tables as well as views, but no tables. Because again, you're not writing to the SQL pool. This isn't a dedicated SQL pool, which is going to store your data permanently. This is just a waypoint for your data. If you don't have a database, you can create one by add new resource and select SQL database. And then that'll let you select the pool type. And I don't actually have a dedicated SQL pool connected to this workspace. So I could create another serverless pool should I wish. So I've got this database already in place, and I'm going to use openrowset and connect to my data lake, query Mars Farming raw errability score 1.text, and get back the top 10 rows. As I do that, I get, not surprisingly, 10 rows worth of data. Took about 3 seconds to process. And if I select messages, there's a couple of things that I do want to prime you for, and we'll talk about it a little bit more as we go on, but total size of data scanned. So let's jump that up just a little bit so you can see it better. 7 megabytes of data scanned, 1 megabyte of data moved, 0 of data written. Remember, the model is price by data processed. So that type of information, that's going to give me a feeling for how much money I'm spending overall in order to run this query. And we'll tie that to specifics in a little bit. But for now, let's look at this third script. We are going to select the distinct set of years from errorability_1.txt. So the format of this file is still the same. Oh, you're not seeing the demo. Uh-oh, let me reshare. I thought I shared the entire screen and not just a window. All right, that's what I was doing wrong. So let's start from the beginning. Creating a database, I can select add new resource and SQL database. And if it's a serverless database, type in the name, go forth and have your database. Dedicated, I would need a dedicated SQL pool, which I actually don't have set up here because I don't need servers where I'm going. The database Mars farming, I've already created it, and it has, as I mentioned, external tables as well as views and some resources. In order to query the data, we saw this script that I walked through in the code example, and reading from errorability_1.txt, I get back the top 10 records of data shaped in this particular format. And here are my 10 records. Selecting messages from here shows me the total size of data scanned, moved, and written. So again, we're going to keep this concept in mind because this is our method of payment, or what will drive the payment required. So now we have the distinct set of years. So I can use the year function in T-SQL and load this data called errorability. So this virtual table is called errorability. And I'm saying essentially the year of errorability.reportDateTime. And I get back the 5 years of this data set. So, all right, next query, something simpler. What is the highest errorability score in all of this data? And I've changed the location. So if I go over to data and select linked, I can see my linked storage account. Inside here, I have Synapse. So this is my container that I'm going to care about. And I've got a few folders of interest: raw data, some curated data, and metadata. The raw data is broken out into 7 separate measures, and we already saw errorability_1.txt. So this is roughly 7 megabytes, and I can preview the data and see this is what the raw data looks like. It's just semicolon delimited data. The curated data is the same information, but it's in what I would consider a much friendlier format, and for a couple of reasons. One is that we have data broken out by year and then by month. And within each month, I have a collection of Parquet format files that I'll be able to use to retrieve data within that month. And I'm going to look in the year 2117, all months, all .parquet files, and get the maximum errorability score. One thing I do want to mention, with CSV, I specified a with clause and indicated here are the data types, here are the sizes, and here are the attribute names, the column names that I want to use. With Parquet, that's not required because within the metadata of Parquet files, we already have information on the types, the data column names, and so we don't necessarily need to repeat that. That makes this a simpler query, and we get back our result of 1.03 is the highest score. It did take 17 seconds to complete. Had to go through and process 34 megabytes worth of data and return back the single row that was of interest. In addition to reading CSV and Parquet data, I mentioned we can also read JSON data. But I also said, well, this is a little bit weird for JSON data. And let me show you what I mean by weird. If I open up this metadata, let's check out outcome.json. It's a very short script. If I preview the data, it's just 2 rows. This is the way that Azure Synapse Analytics wants to read JSON data. It is technically not valid JSON. This is valid JSON right here. That describes an entity that has 2 attributes, outcome ID, outcome name. And each one of those has a value. So that's technically correct. But because I have 2 of these, they should be in an array with square brackets and comma separated to indicate where each element is. Azure Synapse Analytics does not want the array. It doesn't want the separated elements. It wants 1 row per element, because the script to read this data actually is a little hacky. It is a hack off of the CSV file reader. It's reading and using this particular terminator and field quote. This is the indicator to that formatting engine that this is not a regular CSV. This is not a regular delimited file to read. This is a JSON file, and each row is now treated as an element that should begin and end with open and close brace respectively, and should have the defined elements within. We're going to pull in this data as a document and read out the values of that document, a JSON value of outcome ID and outcome name. If I run this, what we're going to see is that it parses each row separately, and then from there I can use JSON value to pull out the elements. A little bit weird to do, though it does work. And for a less trivial version of this file, I have plot data, and this plot data includes the plot ID, the owner, which, by the way, there's a separate owners table, the city in which it's located, and the size in acres. So we can see how large each plot is, where it's located, and who owns it based off of this plot.json file. That's one way to read data using openrowset. It's not the only way. You can also create external tables using Polybase. Azure Synapse Analytics takes an existing Microsoft data platform technology called Polybase and has its own extensions on it. So Polybase was already a part of Azure SQL Data Warehouse and now dedicated SQL pools. But you can also use it with serverless SQL pools, specifically when querying data in Azure Data Lake Storage Gen 2 and also Cosmos DB. If you'd like to learn more about Polybase itself, specifically on-premises SQL Server 2019 Polybase, check out this link, csmore.info/on/polybase. I have an entire talk on the topic. I actually also have a whole book on the topic if you're really dedicated. It's called Polybase Revealed. But we don't need a book to get through tonight. We just need to talk about 3 types of external objects which are relevant to Polybase. The first one is the external data source. And this is going to tell a serverless SQL pool where it can find that remote data. This is a pointer to where the data lives. It's not the data itself. To create an external data source, it's fairly simple. We just say create external data source and give it a name. And then we give it a location. In our case, because we're reading from a data lake storage, we just have to reference the location of that folder. And unless your data lake storage account is open to the public, which most of the time it shouldn't be, we're going to need some sort of credential. The credential that we're going to use is a SAS token. And to create that credential in our serverless SQL pool, we create a database scoped credential that I called SAS token, right? Its identity will read shared access signature, and its secret will be the SAS token that you generate. Incidentally, this will not work with on-premises SQL Server. I wish it did, but as of today, SQL Server 2019, you cannot use a SAS token to read data from Azure Blob Storage. You can, however, use it within a serverless SQL pool or a dedicated SQL pool in Azure Synapse Analytics. We've created that link to where the data is located. The next step is to specify what is the shape of the file. What is the format of the file? We can use one of a few different methods. Delimited files and Parquet formats are going to be the 2 that you'll probably land on. Delimited file format, it's pretty simple. You create an external file format. You say, hey, this is delimited text. And you specify some format options, such as this is comma delimited, so the field terminator is a comma. This is UTF-8 encoded as opposed to UTF-16, and so on. For Parquet file format, it's even easier. You specify the format type is Parquet, and the only attribute that you could set is the data compression. And there are 2 different data compression settings for Parquet. There's one that's a little bit better compression, and there's one that's a little bit faster to read. So essentially, that's your trade-off. Slightly faster, slightly less disk space used. We know where the data lives. We know the file format of the data. Now we want to understand the shape of the data with respect to the individual columns. And that's where an external table comes into play. SQL pools require structured data. We can talk about Hadoop and Spark and the concept of semi-structured data, where I can read this data in one way, process it, maybe I handle it different methods. Doesn't work for a serverless SQL pool. It's got to be structured, just like a regular table and on-premises SQL Server must have appropriate shape. And the type of shape that we're looking for, we have a create external table statement, and we specify column names and data types. Now, unlike pretty much any other version of SQL Server or SQL related product, we do not specify null or not null. If you put in not null, you will get an error that says you can't have not null here. If you put in null, you will get an error that says you cannot have null here. You don't actually get to choose. The engine makes this nullable, but takes away your ability to state one way or the other. So we don't specify null or not null in this create statement. We do specify where is the data located. So I have this data source, Mars Farming Curated. That's my pointer to some folder. And within that folder, I can go to subfolders and then eventually to either a single file, a collection of files, or a folder. And we specify here is the file format. These are Parquet files. I want to read all the Parquet files in Errability Score January of 2120. So 2 different techniques, openrowset, external table with Polybase, but we can combine the 2. And this gets to the limited capability within a serverless SQL pool to modify the external world. And that is the CTAS statement. Create external table as select. And here I can shape an external table before I write to it. Let me show you what I mean. Here we've got a create external table statement, just like the one before. I have the location, the structure the same as before. The difference is we are creating one as, instead of here simply stating here is where the data lives, we are going to generate a new external table based off of this query. Select star from openrowset, go read the data in Errability Score, every text file in there. It's all in CSV semicolon delimited format. So that's all of the files in there, all the text files in CSV format, semicolon delimited. It's got a particular structure to the data, plot ID, report date time, Errability Score, and I can also use a where clause because this is at the end a select statement. So this is a standard query. I can say where report date is 2116 and report month is 1, January of 2116. And this query will create a new external table available in the SQL pool. It will pull the data from all of the Errability Score files, will do whatever processing we have specified, and will write the results of that to this new folder. So this is the one place where we can modify data. That's the way that we modify data. But it's really useful if, for example, I want to take this data and reshape it. I mentioned that all of the raw data here is by plot, and it's in text CSV format. Well, I want to make this in Parquet format, shaped by month. So this is the way that I did it. And I can even show you down here in the load script. I actually had a simple bit of dynamic SQL that would loop through the different months and the different years because I knew where the beginning data was and where the end data was. And I could create one external table for each month, reading all of the Errability scores, processing all of that information, writing out for that year and month, and executing the SQL statement to generate that new external table for me, which also wrote out in the curated folder all of these things. So I kind of bootstrapped my process to curate the data. A slightly simpler way of doing it. I have here a master key, a database master key, so that I can store database scoped credentials. I created one for that SAS token write. So I have a SAS token that allows me to write data into my curated folder, as well as list files and read data from there. I've created an external data source going to the curated folder, and that Parquet file format using a snappy codec, which is a little bit faster as opposed to a little bit more compressed. And creating our external table, this is just taking data that already exists, making it available to me in external table form. So let's execute this. And give it a try. Select top 10 star from this external table. As far as an end user is concerned, this query is just a regular SQL query. And I can also obviously specify with a where clause. I can join to other tables. I can treat it almost as though it were a regular table, with exceptions being can't insert, update, delete, merge, truncate, can't modify any of the data. But I can write queries against it as though it were a table that were actually there available to me. I do have a script to run a CTAS statement, but this one takes a little while, so I'm going to, for the sake of time, run right past it. But I'll give you a link to where you can get those scripts later on in case you want to check that out. Okay, let's close all other tabs. And talk about spelunking. Serverless SQL pools, like I mentioned at the beginning, I think their best use case is this sort of ad hoc data exploration. You can query arbitrary files, arbitrary folders, look for connections that you may not have thought about, and not need to do all of the brunt work of making this a part of your data warehouse. If you want to run these queries over and over and over, then it probably makes sense to make them part of a data warehouse. But as you're exploring, you want to be able to explore without a lot of burden. And one of the ways that we can explore is using what are called file path searches. Openrowset queries, as we saw, can load data from a single file. That works pretty well. This was one of our first queries that we ran. But we can also use the wildcard character asterisk to make this a little bit different. We can include a variety of files. So this first highlighted bulk statement, give me all of the files in Errability Score. The next one is, within Errability Score, give me all of the files that start with the name Errability Score underscore and end in .text. With this third one, show me everything that begins with Errability Score underscore 1 dot whatever file format. That could be text, it could be Parquet, it could be maybe some of them are .txt, some of them are .csv, some of them are .tbl, whatever. As long as they're the same format, the same structure. In this case, we're going to load everything, every one of those files that fits this pattern. But it's not just the file names and the file types that we can use pattern matching on. We can actually go a little bit further than that. One thing that we can do is say, include everything star.parquet. And then we can call the file name function on our virtual table and get the file name associated with this row, with this data. And here I've got file name and the count of rows, and I group by file name. So that's actually going to give me per file how many rows are in this file. And if you look at the bottom, you can see this finished in 2 seconds. That's pretty fast. And it's that fast because it did not have to scan through all of the data. Parquet file format includes metadata, which also includes the number of rows in that Parquet file, which means that this was able to just parse the metadata and return back, here's the file name, here's the information from metadata, this is a valid Parquet file, we're good to go. So it doesn't need to scan through everything. That's going to save us time. It's going to save us money. We can also include multiple wildcards at different levels. Here I've got show me every year, every month, every Parquet file. And I can use the file path function and specify which asterisk I am talking about. The first asterisk is the year. The second is the month. The third, which I don't reference here, is the file name. So I have file path 1 as year, file path 2 as month, and the count of records as number of rows. How many records do we have per year and month in this data lake? And this took about 4 seconds to complete, going through the entire data lake, which admittedly is not enormous. It's not huge by any means, but each month had about 40 million rows for errorability score. And we can see those results very easily, just 4 seconds. So again, it read the metadata for all of those files, processed that metadata, appended on these attributes, year and month, that are part of my virtual table now. So it's almost as though I have year and month as columns someplace, and allowed me to group by them. What's even better is I can include this in the where clause. So I can say, give me the year, month, and number of rows for all of the files where the file name begins with a C. And we get back the 4 months, which have file names that begin with C. And we see how many rows there are for files beginning with the letter C. If I want to take some results and work with them elsewhere, I can export that data within the Synapse workspace. Select Export Results. You can bring them out to CSV, JSON, or XML. There is also some rudimentary charting capability that's kind of similar to what you can get in Azure Data Studio without Sandance. Here I have a scatter chart of size in acres for the first 10 plots of data, showing you that everybody's got roughly 40 acres and one cyborg mule. So let's take a quick look at some of this stuff. Okay, we're in Errorability Score 2120 January, the Parquet file format, and we're going to get back the file name and number of rows. This is just to show you that the examples that I have were not altered in any way. It's something that's easily replicable. I have all of these files. Some of these start with a C, and each file has so many rows. If I want to use file path, I can specify asterisks in here, specify file path elements, and assign them names in the select clause. I can group by them, and we can get back per month, per year, per file, how many rows were there. Well, each file obviously is going to exist in 1 year and 1 month. So the cardinality is the same as the prior query. And I have January 2119. I've got obviously a lot of different files. If I just care about year and month, I can remove file name from the select clause and as well as the group by clause. And within about 4 seconds, I'm going to get back my results. So here, 40 million rows. If I scroll down a bit, it turns out that not every month had 40 million rows in it. Some of them had as little as 36 million. We can also filter on specific file names. And that's my where clause, where errorability.filename is like C as in Charlie. We get back some results. If I want to work with some of these results, well, this is where visualization can come into play. What I have here are plots. So we go back to the JSON openrowset operation, and we get back data on each individual plot. And so I see plot ID, owner, city, and size in acres. If I want to connect together different virtual tables, I can use subqueries or common table expressions. I think it's a little bit clearer to see them as common table expressions, So we have one that I call plots and one that I call O2 level, or the oxygen level. Per plot across all 5 years worth of data. And I have a plot ID and the average O2 level. Then what I'm asking is, what is the average oxygen level per city in our terraformed Martian colony? And if I run this operation, we can see that I'm joining O2 level to plots as though they were just regular tables. And I'm going to get back my results. Probably, I think it takes about 16 seconds to get this data. There we go. And we can see that all of them are in roughly 19 to 20%, which is Earth level. So well within range for humans. I can select chart, and it gives me a very unhelpful line chart because it doesn't recognize what kind of data we have. I'm going to change that to a bar chart. My category will be city. My legend will be average O2 level. And now we can see the city that has the largest average O2 level and the city that has the smallest average O2 level. And like I said, 19 to 20%, humans can breathe that, no problem. So let's talk about logical data warehouses. Historically, we've built big data warehouses. It takes years to build these things. We work with all the different product teams across an organization, have them struggle to come up with common, meaningful names for facts and dimensions. We try to conform our dimensions and hopefully get a system which lets us generate relevant reports on a regular basis for known business problems. But what if you don't necessarily need to do that? One approach to this problem is what Databricks calls the data lakehouse. The data lakehouse essentially says, how about instead of building up a separate database, we query the lakehouse or the data lake as though it were a warehouse. And the way they describe it is, historically you have this data lake that has structured data. Maybe you've got relational databases, as well as semi-structured data like text files, Parquet format files, as well as some unstructured data, images, videos, music, audio. And you may have machine learning operations where you process the data. You may run it through a vectorizer. You may transform the data into matrices so that you can run gradient descent boost. Then for the business people, we have an ETL process. That ETL process builds out a nice data warehouse or maybe some friendly data marts for a specific business unit. And those drive the reports that they view. It drives their Power BI utilization. It drives how they connect to that database in Excel and get the data they need. So this is the existing model as it is today. The lakehouse model is a little different. The idea here is, again, all of that data sits in your data lake. Structured data, unstructured data, semi-structured. And for each one of these uses, instead of having an ETL job that puts the data in a database, we query the data lake to get the results that we need when we need them. Now, I think this is an interesting aspiration. I would not bet my career on this today. In fact, I would bet my career on this not working today. I don't know of I don't believe it is fast enough for any meaningful business to adopt the lakehouse. The queries are just too slow for realistic data sets. They would work for my demo, but then you start getting to actual corporate data sets and expectations of, I want this data really fast, and it all falls apart real fast. So that's about the only thing that's real fast about it today. That said, there are some really smart people working on this, and I am confident that 3 years from now, we'll be able to look at the data lakehouse and say, yeah, this is a viable model. I don't think it's a viable model for most companies, for pretty much any company today. So that's one approach to trying to simplify the warehousing experience. A serverless SQL pool is a different approach to that, and that is to use this concept of a logical data warehouse. There are some similarities in the approach. The data still lives in the data lake. The data lake is the thing that gets queried. But what happens is that we create views that represent what the data warehouse would look like, and then we query those views. So let's take a quick look at that. Close everything but Synapse again. And let's hop here. For each one of the different measures, air ability score, carbon dioxide, nitrogen, oxygen levels, the soil pH, temperature, ground temperature, and water quality, we are going to create a view that hits air ability score, year, month, file name. We're going to include all of the relevant columns. And just for the sake of clarity, I included them here, but it's not strictly necessary. And I will also include file path for year and month. So I create one of these for each of these tables, as well as one for my plot JSON script. And if I hop over to the database, I already have these views created. And if I look at a view, it just looks like a view, a SQL view. So there's nothing special to it. And if I query the data, there's really nothing special to it. If I select top 5-star from water score, this is a view that's going to read from my data lake, all data, and return back whatever needs to be returned. It read 4 megabytes worth of data, moved 1 megabyte, and then gave me back the top 10 results, which includes that year and month, by the way. Now, if I want to join all of these together, I have plot joined to air ability score on plot ID, and I have joined to CO2 level, and I know that each one of these indicators sent out a signal every 10 minutes. I know this because I generated the data. Makes life a lot easier when you can make the data up. We're going to interjoin each one of these tables together and get back information on the different measures. So for each plot, what is the city? How big was the plot? What time frame? And all of the different measures, where report date time is 8 a.m. on March 15th, 2118. And I have a whole bunch of ands here. What we're doing in this case, let me just run this query so that it can get going while I talk about it. What we're doing is specifying use this year and this month, because by its nature, this where clause is not specific enough for the data lake to understand, or for the serverless SQL pool to understand that the only place where there is data which matches this is in year 2118 and month 3. To get around that, I specify for each one of these views, just look at that folder. So within year 2118, within folder 3, only look at that. That way, instead of scanning the entire data lake, we're just scanning 1 month. And it took half a minute to give me back my results, but I was able to get each one of these scores, and processing was about 230 megabytes, which is a lot less than it would have been if I didn't include these. If I didn't include these, by the time Q&A was done, maybe this query would have finished. As far as security goes, let's talk real briefly about that. Serverless SQL pools aren't going to have the same breadth of options as on-premises SQL Server would, because there's not as much that you can actually do in terms of modifying data. But still, there are some controls that we have, and I'm going to talk about 6 of them, starting with controlling your data lake. And one of the easier ways to control that is you create SAS tokens and specify the permissions within that SAS token of list data, read, or list files, read data, write data, delete files, etc. So I can create a SAS token by right-clicking on one of the folders within a container, and I can generate SAS token. I can take that SAS token and save it as a database scoped credential. And that way, you may have a SAS token that's for writing, a separate SAS token that's just reading and listing data. Then certain groups of people get the write capability where they can use CTAS to create a new folder. Others just get the read capability to read data that's already there. And you can specify those roles by creating roles. So I can create several roles within this database and add members to those roles, just like you can with a regular SQL Server box product. Once you have roles, or if you do want to do this off of users for some reason, you can grant permissions to objects or to those roles. So for example, if I have a view called my view, let's grant select on that thing to the analysts. Maybe I want to grant select on everything in the DBO schema to analysts. And perhaps the analysts need to be able to use CTAS statements to write new folders. So let's give them a reference to this credential so that they can do that work. If you want to allow people to use openrowset, this is a bulk operation. We saw the word bulk in there for what data gets loaded. So to allow this, you must grant administer database bulk operations. This is unlike on-premises SQL Server. This isn't really that big of a deal for permissions, because really the only thing you can do with it is openrowset. But if you don't want to allow people to arbitrarily query your data lake, then you could deny administer database bulk operations to a group, and now they can use the views that you've created, but they can't create their own results. They can't create their own openrowset operations in order to look at data within the data lake. If you want to give somebody full control, the command is grant control. You would do that for administrators. You wouldn't do that for everybody, hopefully. By the way, full control means you can set up permissions. You can change the permissions. You can create or destroy external tables and views. You can query data with openrowset. You can basically do anything in a serverless SQL pool. There is no such thing, strictly speaking, as row-level security in serverless SQL pools. What we have, though, is the ability to kind of sort of get row-level security using views and optionally an inline table valued function. So let's suppose we have a role called North Armstrong Analysts. So analysts for the city North Armstrong. We've added Fritz to that. Fritz is an analyst just for that city. But we don't really want Fritz to see the other cities. What we can do is create a view which selects star from all of my arrayability data, where the username is me because I am special, or you are in the role North Armstrong Analysts, and the city name, which is, by the way, one of the columns in this view, is equal to North Armstrong, or you're a member of this other group and it's that city name. So this is a check on a row by row basis for each city name and each role. This can get a little complicated, it can get a little large. So one alternative is perhaps I create dbo.arrayability is select star from openrowset this data without the where clause. So that is dbo.arrayability. Then I create a function, city analyst. And essentially you give me the city name and I'll tell you, are you eligible to view this row? And I'll return 1 if you're eligible to view. And here are the criteria that determine whether you're eligible to view. So sorry, quick typo. This is at city name. Then I can cross apply dbo.arrayability, which does not have that long where clause, cross apply to city analyst, and when the function returns a value, then we'll return that row as part of the select clause. So this may be a view called secure.arrayability, and we grant select on secure.arrayability to all of our analysts. And then that row level security kind of handles the underlying operation of, do you get to see this row? It's a bit more effort, but that's what we have today. Last bit, the money. How much is this actually going to cost? And I mentioned $5 US per terabyte processed. But what does data processing mean? Well, it's made up of a few different things. Data and metadata that is read. So if you read metadata from a Parquet file, that costs money. If you read an entire Parquet file or an entire CSV file, it costs money. If you use eager spools, lazy spools, if you create temp tables, it's going to cost you money. Data that's written to storage as CTAS costs you money for reading, costs you money for writing. Data that is transferred out, so transferred between nodes, between servers in the serverless world, or that is sent out to the end user as part of a result set, costs you money. Each query has a minimum cost of 10 megabytes of data processed. If you process 1 megabyte of data, you're charged for 10 megabytes of data processed. So as such, try to avoid an enormous number of tiny point lookups. This is not an OLTP system, and I recommend not trying to treat it that way. Let's talk about how we might save a few dollars. There are 4 techniques that I'm going to talk about to try to save some money as you're querying data in a serverless SQL pool. The first one is to use the right format, which generally speaking will be the Parquet format. For a couple reasons. One is that Parquet will compress data better than CSV will. It also includes column metadata, and we've seen a few cases where we can read the metadata, get all the information we need without needing to read the entire data file. Also, if you do need to read an entire column, let's say that we've got 25 columns long, but we only need 2. I can read those 2 because the data is stored in a columnar fashion without having to read the other 23. This is unlike CSV, where I need to read the entire row, break it up into columns, and then now I can pull out the 2 that I need. So for those reasons, Parquet will usually save you a bit of scratch. The downside to the compression that Parquet allows is that not everything can be compressed. And let me give you a specific example. Suppose that we've got Parquet data. It's 5 terabytes uncompressed, and then we compress it down to 1 terabyte in our data lake, which is great. I love that. If your query selects star from that 1 terabyte and then just returns everything to the end user, you are charged 1 terabyte to read that data off of disk. It is then uncompressed and then read out, sent out to the user, and that is 5 terabytes written out because it's now uncompressed. That is a 6 terabyte charge. In other words, that's $30. By contrast, if you don't write out all of the contents to the end user, you could possibly save quite a bit of money. Let's say you still read the full terabyte, but maybe you aggregate the data so that it's down to 100,000 rows of numeric data, or short, like relatively small amounts. At that point, you might be talking about 1 terabyte plus a few megabytes, 10 megabytes, 20 megabytes. So $30 query, $5 query, just because you aggregated the data. This is when you start talking about real money. Much smaller result sets give you lower prices, and by the way, also will give you the data faster. So faster performance, cheaper cost. Do perform that file name and file path filtering. Anything that you can do to tell the processing engine, don't look in this location, will save you money, because it won't look in that location, it won't read those files. Also, if you're using openrowset, you also want to narrow down to the smallest number of folders or files. It'll make querying a lot faster, it'll make querying a lot cheaper. If you have certain aggregates that are used quite often, let's say that we look through and we need to calculate the average score on an hourly basis, and we hit that every hour, it may make sense to pre-calculate those results and store them in a folder someplace. Then you just read the pre-calculated results once an hour. And for each new hour, you calculate and you write it out to that folder. And again, you query it. Now, instead of processing potentially a lot of data every hour to get you the same results plus one new row, it ends up being a lot cheaper, because hopefully, you're writing, it might be just one row per hour, and you can read that much smaller pre-aggregated, pre-calculated result set. And you may also note that if you're using a file format like CSV, serverless SQL pools will pre-fetch data. They will read ahead in order to improve performance. So perhaps you're getting the top 5 rows from a file, but it may actually read the first 50 or 100 rows for performance's sake. You will be charged for that extra number of rows. Typically, that's not going to be an enormous amount, but over a certain number of queries, that amount can add up a little bit. To reduce this, you can store data in Parquet format as one example, and then write queries. Ideally, write a query which is intended to read just the metadata or the entire file, or at least one column in the entire file. This may involve some reshaping of the data, reshaping your data lake, working off of how you expect people to query the data. So that may be a little bit more, say, constraining than you want to give for a serverless SQL pool. But if you're really concerned about eking out every possible penny, this may be a route that you want to take. If you want to figure out how many pennies this is all costing, there is a DMV, sys.dm external data processed. And let's take a look at that DMV as our last demo. We're going to figure out how much money I've spent today doing this demo for you. So DM external data processed, I have the type data processed in megabytes, and $5 per terabyte. So megabytes divided by 1024 squared as my approximate cost. Today, doing all of this, it has cost me approximately 1 penny to do today's work. Over the course of the month, I have spent a whole 5 cents because I have processed roughly 10 gigabytes of data. So this is not going to break the bank. Certainly not at the levels that I'm using. But as I mentioned, if you start working in hundreds of terabytes or petabytes, and you just allow scans of the entire data lake or all of your folders in the lake, those prices can go up very quickly, especially if you don't look in metadata, if you don't filter down to specific folders and files as you can, then you can start talking about real prices. If you have $5 per terabyte and you have a petabyte of data, and heaven forfend you scan the entire thing, that's $5,000 just to read. Mind you, if you write it all out, that may be another $5,000. So that's a $10,000 query right there. So serverless SQL pools really benefit people who are able to plan ahead a bit, who are able to think about the queries that they write. And as such, it's something that you'll want to think before you hit F5. This isn't like an on-premises server where worst thing that happens is that everybody's inconvenienced because all your queries are slower now. Here, bad queries have $ attached to them. So this has been a look at serverless SQL pools within Azure Synapse Analytics. They are in the SQL Server family, but even though I've made a lot of comparisons to on-premises SQL Server and by extension Azure SQL Database, they're not that closely related. There are a lot of differences between the two products. If you want to grab these slides, if you want to grab the scripts or links to additional resources, go to csmore.info/on/serverless. If you have any questions at all, please feel free to drop them into chat. If you don't want to put them in chat, here's my email address. There's my Twitter handle. And with that, I want to say thank you, everybody.